Course material today I am going to cover from this module online stream analytics. From there I already covered the anomaly detection, the first part. So, I will start with the second part. And today is the last day. So, today I will talk about some of the stream analytics work that we did in the past here at UT Dallas, some of our research, and from there we got a pattern, and the pattern we are hoping that some company will buy that pattern or something. So, we are waiting. And this work was funded in the past by NSF, Air Force, NSA, those agencies. So, yesterday Professor Roggio talked about advanced analytics, more specifically LDA and then Bayes network. So, he talks about more math. So, I will talk about a little bit math, not that much, but anyway. So, in the past I introduced you what is the stream mining. So, just for completeness I will talk about that same thing. So, after finishing this lecture you should be able to understand what is stream mining and understand the new concept called novel class detection, and that is also known as a concept evaluation. So, we will talk about that more details. So, again what is data stream? Data stream means continuous flow of data that are continuously coming, like network traffic where the packets are coming one after another, that can be treated as a stream data. And from the network traffic, let us say our goal is to identify whether incoming traffic is benign or malicious. So, in that case we can treat the stream problem as a classification problem. And then sensor data generates humongous amount of data continuously, like this devices in the past showed you that IoT device generates the continuously the data. So, that can be treated as a stream data. And then in the social network we post messages that can be treated as a stream data also. So, as I told you before, in the last 4 days we are trying to tell you that when you run the analytics algorithm, analytics can be two types. One is supervised learning, other one is called unsupervised learning. Supervised learning, there we can talk about classification problem more details, and classification is a supervised learning where we need a ground truth and so on. On the other hand, I mentioned that clustering can be an example of unsupervised learning. Clustering is unsupervised learning because we do not need any ground truth or level data to build the model. Basically, we group similar data points together, those type of things. So, in this work we will focus on the classification problem. So, basically incoming data we want to label it whether it is a malicious or benign. So, think about this. So, it is a classification problem. So, we will have some ground truth to build the model, what we call it, use the past label data to build the classification model or classifier, and when the test data comes we want to do the prediction. But it is not like that exactly, but this is very basic idea, and this classification can help us for decision making. And here is an example I want to demonstrate. In cybersecurity context, network traffic comes, it passes the firewall, right. So, then firewall will have a bunch of rules. So, if you know that network traffic has a header and the payload. So, in the firewall we may mention if the traffic comes from a particular source IP, let us block the traffic, or if it targets particular port, then block the traffic. So, in the firewall we mention bunch of rules, but there is no guarantee that when the traffic passes the firewall, the traffic will be always benign. It still might be malicious. So, our goal is to apply some classification model here. When the traffic passes the firewall, still we want to label the incoming traffic whether it is a benign or malicious. If it is benign, it will go to the server. If it is malicious, we will do the further analysis. Now, the problem is in a stream, this let us say you build a model at the beginning of the year, and then you try to use the same model at the end of the year also, then what will be the problem? You know that attacker is not dumb. They will come up with a new attack patterns. So, in the classification model, what we try to learn? We try to learn some patterns, right? If you see this pattern, just block the traffic. If you see this pattern, allow the traffic, something like this. Now, so this model is built on the first week of data, and then we try to test it in the still we are trying to use this model for the prediction at the end of the year. So, that there is a possibility that model may be obsolete over time. If the model is outdated, then what will happen? Then there might be a new attack, and our model may be classified as it will classify this incoming traffic as a benign. If it is benign, then it will go to the server and damage the server, right. On the other hand, so the point is we need to update the model. This is the key point. Now, the question is when you want to update the model. So, can you suggest something when we can update the model? So, one possibility is update the model means what are the things will be involved. So, there are two questions. One question is when do you want to update, and when do you want to update the model? That is one question. And the second question is how do you want to update the model. So, with regard to first question, I will explain in a minute how we can update, at which point we will update the model, and then when you update the model, what you need. When you update the model, what you need? Basically, you need more ground truth to build the model, more training data to build the model, more training data to build the model. And then next first question is at which point you will update the model. Can you tell me at which point you can update the model? There are various ways you can design. One is so there are two questions, when you will update the model and how do you want to update the model, basically how you want to provide the ground truth. So, when you want to update the model, there are two ways you can do it. You can update periodically. Periodically means every 1000 instance you will have, you will update the model. Every 1000 instance you will have, after prediction, you will update the model. So, test data comes, you will do the prediction first. So, in this case, you will do the prediction first, and then you assume that somebody will give you label on this data, then you will update, you will, once you have the label from this data, you will update the model. So, every 1000 instance, maybe you will update your model, or periodically also instead of 1000 instance, you can say at the end of the day 1, you will update the model. At the end of the day 2, you will update the model. At the end of day 3, you will update the model. So, these are the options you have. But and then another approach is on demand. When you feel that you need to update the model, at that point you will update the model. If you feel that your model is doing perfectly all right, so at that point you do not need to update the model. So, let us say here you are updating the model at the end of the day 2, but the current model is sufficient. You do not need to update the model. Basically, current model is perfectly all right to predict the incoming data. So, in that case, what will happen if you update the model? Basically, you are wasting your resources, because you need to train your model and you ask the human to give the labels, annotations and so on. So, human will provide the annotation that is costly, and also you are running a program for training purpose and so on. So, that way you are wasting your resource. So, today I will talk about So, first part of my presentation, I will focus on the two approaches, periodically and on demand both. So, you can update the model at the end of day 1, at the end of day 2, at the end of day 3, what we call it periodically, or at the end of 1000 instance, first 1000 instance you will update the model, second 1000 instance you will update the model. So, that way you will departition the data. And for this approach is simple, it works well, but it has some overhead, because there is a possibility that current model is fine, but still you are updating the model. That way you are wasting your resources and ask human to give the levels and so on. So, that is why the second approach was designed, we call on demand basis. When you on the fly, we will determine whether we need to update the model or not. If we can determine that this is the right point, we update the model, then we will ask the human to give the levels. So, be aware of it. I am going to explain those two methods in details in a minute. So, first I will focus on the periodic update. And then second problem is how do you provide the ground truth. At that point, when you want to update the model, you can assume, one possibility is you can assume that human will get the human will provide the labels for this data, and then those labels will be used for training. But keep in mind, when human provide the annotation, it takes time, right. If you have a 10,000 data points you are getting at the end of the day, and you need to, so day 2, let us say you gather 10,000 data points, and your model predicts all of this 10,000 points. Now, you need to provide the label for this 10,000 points to retrain your model or to build the new model. Then in that case, what will happen? Either you have to hire many annotators, more than one human to provide the labels, because a single person cannot do the annotation in a single day 10,000 data points. If it is a text document, or if it is a traces. So, you need more money, those type of things. So, can we do, in that case, the idea here is instead of using all the training points to build the model, can we use selectively few points for the labeling purpose. So, what I am trying to say, one possibility is I can use all of these data points for training, basically 10,000 label I will use for the training, or can I selectively use few points from there, let us say 500 points from there, and ask the human to give the label, and then from there we build the model. That is known as in a machine learning area called active learning. Just I give you a heads up. Let us say the system predicts each of this point whether it is a benign or malicious, right. So, when the day 2 I have a 10,000 points, and system will try to predict each point whether it is a benign or malicious. When it predicts yesterday and then before we try to tell you that when system predicts, it will predict with a certain confidence or probability, right. So, if you remember in case of naive Bayes, the simple classifier, that gives you some probability, right. So, when you predict, let us say it belongs to the benign class or it belongs to the malicious class with this probability. So, now if the data point is predicted as a benign class with a very high probability, then what you can expect? You can expect that this prediction might be correct. On the other hand, a point or data points has been predicted as a benign class with a very low probability, and attack class is also very low probability. Then you can assume that this might, the classifier may not be sure about this. You can ask the human to give the labels. So, that is the idea of the active learning. Instead of using all the data points for and ask the human to give the labels, you will selectively ask only few. You will select few points somehow, and those points you will ask the human to give the labels. So, basically if you feel classifier is very confident in the prediction, then for those points you will not ask the human to give the labels. On the other hand, if you feel that classifier is coming up with the prediction, but with a very low confidence value, then in that case you will ask the human to give the labels. So, that type of thing in the active learning we can use. That way we can handle some of the issues for the during the training time. Okay, I will talk about those more details in a minute. Do you have any questions so far? So, this picture I just try to demonstrate you that we need a classification model, and in stream case this classification model needs to be adaptive in nature. So far whatever the homework or hands on we covered, always we build a model and try to use it forever, right, that same model. But I am saying in real life the model may be outdated, so you have to update the model. And stream introduce bunch of challenges. The first challenge is called infinite length issue, concept drift, concept evaluation. I will talk about that more in a minute, more details. But do you have any questions so far? No? Okay. So, this tells you that stream data is different from the static data. Static data means you have a bunch of data points and you can and that is it, and that is the boundary, you do not have any more new points will not come. So, you can load the data from the disk to the main memory and build the model, those type of things. That way we always train the model. In case this homework, if you remember, we said this is your training data offline. So, you build a model and then you try to test it, right, for this IoT device experiment anomaly detection. So, here we are saying data are continuously coming. So, what will be the potential problem? So, when you run all these machine learning algorithms, if it is not in a distributed environment, if you run machine learning algorithm with a single computer, where what do you assume that where the data will, when you run your machine learning algorithm expects input data, right, that input data will sit where? In the main memory or RAM, right. So, now if the data are continuously coming and if you try to run some analytics algorithm, you cannot assume that data will feed into the single machine's main memory or RAM. So, there is a possibility that you can load only a portion of the data. Let us say over time you may have a millions of records will come, right. So, every 1000 instance we will build a model or something. So, I am saying here, so how the infinite length issue will play, this infinite length means data are continuously coming. So, you cannot keep all the data in the main memory. In order to run analytics algorithm, we usually assume that data will feed into the machine's main memory or RAM. Now, since data are continuously coming, so what will happen? After a while, let us say you have a single machine and that machine has a 1 megabyte, not 1 megabyte, 1 gigabyte RAM, and so far 1 week you get let us say at the end of first week you get so far 1 gigabyte, and then at the end of second week you get so far including 1 gigabyte it will be. So, this case you got 3 gigabytes. So, total data size will be 4 gigabyte. So, now if I can easily store the first week of data in the main memory or RAM, let us say. So, that will be allocated for to keep this data in the main memory. But after that what will happen? Second week data we cannot store in the main memory. We have to either move this first week of data to the disk and then load the second week of data, portion of the second week of data will be loaded at the machine's main memory, something like this. So, this tells you that you can store it into the disk, but when it comes to the RAM or main memory, you cannot keep all the raw data. So, what is the solution you suggest?
More RAM.
Yeah, that is fine, more RAM. Yeah, that will be one solution, or distributed computing, or the,
getting out of date, just prioritize the most recent data.
right, yeah. So that's one way you can deal. So why don't you get rid of the old data and just keep the new, most recent data? So that's, but in this case, so basically you will have some policy, replacement policy. Every time new data point comes, you will discard the old data. So you some sort of FIFO you can maintain. But in our case, we want to do the analytics. So what we will do, we will partition the data into a number of chunks. So if I divide the data into a number of chunks, and chunk size is, let's say, fixed. So first 1,000 instance will form chunk 1, second 1,000 instance will form chunk 2, third 1,000 instance will form chunk 3, something like this. Now, when I run the analytics algorithm, I will work first on the first 1,000 instance and build the model and so on. When the next test data comes, I will work on the second 1,000 instance. So that way, when I work on in this data set, this data set will be loaded into the main memory, and the rest of the data set will be discarded. And in my RAM, I will keep the analytics algorithm like the model, support vector machine, or naive-based classifier. That's it. So then once I do the prediction on the second 1,000 instance, and then after that I may update my model or something like this, and then third chunk data comes in the main memory, then all this previously 1,000 instance, what we from the previous chunk, whatever the 1,000 instance I have, that will be discarded or will be purged. So that way we can deal with the infinite length issue. So basically chop the data and load only the portion of the data in the main memory or RAM. Second issue is more challenging, and that has been widely studied in case of the stream mining area, called concept drift. Characteristics of data may change. So without loss of generality, let's assume that we have a two-dimensional data points. So we have a positive instance and negative instance, and we build a model. So let's say this is 1,000 instance, one chunk 1, this is another second 1,000 instance chunk 2, third 1,000 instance chunk 3. And we build a model from this training data, positive instance and negative instance, without loss of generality. Let's assume that we have a two-dimensional data points. And if I want to build a model, in this case, what will be the model look? The model will look like what? Is a two-dimensional data point. So we apply, say, support vector machine to build the model. So in that case, usually support vector try to come up with a hyperplane, right? So in this case, it will be a line due to the two-dimensional points. It will be a line that separates positive instance from the negative instance. Now week 2 data comes, or chunk 2 data arrives in the system. So what will happen? Now we want to do the prediction using this model. So this model will say that above this, the point will be classified as a negative instance, and below this, the point will be classified as a positive instance. Now what happens? Characteristics of data change. So the old decision boundary, what we built in from chunk 1, that is not valid anymore. So the new decision boundary will be something like this. So in that case, according to the new decision boundary, below this all of the points will be a positive instance, and above this will be a negative instance. So therefore, but what we do in this case, we are going to use this old decision boundary for the classification. So in that case, all these blue points will be misclassified, right? Because we are going to use outdated decision boundary to classify the points. An outdated decision boundary is saying above this will be the negative instance, below this will be the positive instance. In fact, this set of points should be this set of points should form what type of class? It should form a positive class, but in this case, if you use the old decision boundary, we will say that this set of points form a negative instance. So those blue points basically will be misclassified. So how we can address that issue? Basically, we need to update the model, right? If you update the model in the week 2, then you can only predict those points correctly. So, this is a problem we face in the stream case, and then so this is the work we developed, nobody has done that before us, and we had a pattern on this. So, here what we call it, let us say in a particular chunk or particular week of data, we have training data, positive class and negative class, and we come up with a decision tree like this. So, in this case we use the decision tree to build the model. The model said it comes up with the 4 quadrant, comes up with these 2 rules. If the point falls into this area, it will be known as a positive class. If point falls into this area, it will be known as a negative class. Do you know which rules satisfy this condition? I mean this part of this quadrant, which rule? So, x 1 will be less than x 1, x is less than x 1 and y is greater than y 1. So, this one will be represents this part of the rule. Now, when the test data comes, these are in this case all this x are test data. So, what will happen according to this rule? So, this part of the x will be classified as a positive class. Do you agree with that? And this set of x will be classified as a negative class, and this set of x will be classified as a negative class. But I am trying to argue that this set of x should not belong to any of this existing class. So, so far in the stream we see 2 classes, positive class and negative class. Now, in the stream all on a sudden new class is emerging, what we call it novel class or concept evaluation. So, when I say concept means class in this case. So, novel class is emerging. So, our goal is to identify this novel class in the stream. Let us say in the stream so far you trained your model with class A, class B, class C instances. Now, test data comes, some of the test data will be associated with class A, some of the test data will be associated with class B, some of them will be associated with class C. But all on a sudden a number of new instances will emerge that may have a not class A, class B, class C in a level, they may have a class D level. So, in that case the class D will be known as a novel class in the stream, right, because the classifier does not have any knowledge about D class, it only knows so far class A, class B, class C, and in the stream now class A, class B, class C instances are coming, and all on a sudden also class D instances are coming, where the classifier is only trained with the class A, class B, class C. That we call it class D instances will in this case will be known as a novel class. So, our goal is to identify this type of novel class. And anomaly detection case, we try to detect, we have only one class so far we see, and if there is that is a benign class, if there is a significant difference from the benign class, we call it anomaly class, right. So, there we usually deal with the only 2 class problem, but in this case we deal with a more than 2 class, we may have a positive class, negative class, and the third class is emerging something like this. So, our novel class in the stream is significantly different from the traditional anomaly detection, where we focus only one class, and if there is a significant difference from the one class, we call it anomaly. Do you have any questions so far? So, what will happen, existing models I mean the models we have we built so far will misclassify novel class instance as a existing class or existing classes. So, our model, the prediction model or predictive model will misclassify all these novel class instances like this as a existing class, either positive class or negative class. So, I am saying these X are brand new class or emerging class. So, when you use the traditional stream classification or machine learning technique, those x points will be either classified as a positive class or will be either classified as a negative class. We cannot say that this x should form a brand new class or emerging class. So, that is our goal in this work we try to tackle. Now, do you have any questions so far? Okay. Okay, now how we build the classification model. There are two ways in we can do the classification in case of streaming. One is incremental learning. So, in later I will show you how we do a lot of incremental learning also, but in this, and the other one is called ensemble based technique. So, in this work we focus on ensemble based technique. Ensemble, you understand that multiple models we will keep or multiple classifier we will keep. But in incremental learning we just keep only one models and we constantly update that model. In the literature it shows that ensemble based technique is more effective. So, therefore, in our work we focus on ensemble based technique. Let us go through the ensemble based technique more details. So, in this case the ensemble size is 3 in this toy example. So, we have 3 models C1, C2, C3 that we built from the training data. And when x data test data comes, like say one test instance x comes, we want to do the prediction. So, keep in mind, just think about this C1, C2, C3, we built it from the first 3 weeks of data. Week 1 data we build a model, week 2 data we build a model, week 3 data we build a model. Model means you apply say decision tree, and decision tree works on the week 1 data or chunk 1 data, decision tree built from the chunk 2 data, decision tree built from the chunk 3 data. Why the C1, C2 will be different? We may use the same set of classifier, say decision tree in all cases, but they end up with a 3 different decision tree. Why? Because we are using the, for each of this model we are using different types of data. So, here we are using week 1 data, here we are using week 2 data, here we are using week 3 data. If you use exactly same data and apply the same classifier, let us say decision tree, then what will happen? All of this classifier will be identical. So, here this 3 classifier will be different because although we are using same type of classifier, this is a decision tree or support vector, but they are taking the input training data is different for each cases. In this case maybe week 1 data or chunk 1 data, week 2 data or chunk 2 data, week 3 data, training data or chunk 3 data.
You're choosing that based upon the resources, right? Week 1, week 2.
No, best resource.
Right, so if you don't have so much RAM, you're choosing those
Right, yeah.
based upon the resources. If you
Right.
have, like I said, more or less, you would choose the classifier based upon how much data you get plus the resources you have, and you choose, okay, this is how we
Yeah. So, that's a good concern. Let us say here the algorithm we try to design, we cannot keep all the raw data in the main memory, so far we see. So, and that algorithm needs to be one pass algorithm. That means data comes and you try to buffer it the data for a time being and build a model and then discard the data and forget that data after a couple of hours, or that is the model we try to follow in a stream. So, data are continuously coming. First you may do some prediction, buffer it window by window data, buffer it, run the algorithms, do the prediction, and then if you have a ground truth you will build the model and then you will forget that data entirely. So, now in this prediction test case what will happen? So, each of the model will come up with a prediction, right. So, here we just talk about binary classification, positive class and negative class. C1 says a positive class, C2 says this test data is a positive class, C3 says a negative class. Then how do you want to combine it in this case? Just simple majority voting, right. Yeah, it will go to the then we do the majority voting, and in this case majority will tell you that this is a positive class, therefore, it will be a positive class. So, that way we do it. Let us say if I use the k nearest neighbor approach and if there is a tie, how do you want to resolve it? If it is an odd number, ensemble size is odd, then there will be no tie, right, if it is a binary class. But if let us say if there is a tie, if you are using k nearest neighbor, then you can take into consideration the distance, or in this case if there is a tie some happens, then you can take into consideration the probability or confidence. Yeah.
Could you also weight the individual outputs?
Yeah, that's possible. Let us say when you do the prediction and you use the k nearest neighbor, you know that k nearest neighbor is a lazy learner, right? So it will remember all the training data, and based on the timestamp you can assign the weight also. If it uses, if the model is, this is the most recent model, I mean this model uses the most recent training data, and this model uses the not the most recent training data, in that case this model may carry higher weight in the voting process, something like this. So if you build a model from the most recent training data, that may carry higher weight in the voting process. That type of thing you can add here also. Okay, so this way the classification will be carried out. So do you understand that classification in our case will be carried out through the ensemble, and ensemble size is fixed. Why you need to fix the ensemble size? That I will explain in a minute. But do you have any other question? Okay, now this way we do the testing. Now I want to do the training, and this diagram will tell you that how we do the training. Again, recall that this training process done at the periodical level. At so we are not talking about demand, on demand, or dynamically we will do the determine that at which point we will update the model. Here we assume that after a fixed interval or after a fixed number of instances we will update the model. So that we call it periodical update. So here for periodical update, this way the update will be taken place. We divide the data stream into equal size chunks. So let us say first, so our case, this is our work. So if you consider the in case of a Spark streaming, how they generate the micro batch or D streaming, do you remember that? You remember in the Spark streaming we said that data are continuously coming, and then we divide. The Spark streaming will divide chop the data into a number of batches, or they call it micro batch. And now what we do not use there the number of instances to generate the batch. The batch size will be determined by time, very good. So by time, right. So here in our case we determine the batch size based on the number of instances, and each batch will have an equal number of instances. So we divide the data stream into equal size chunk, train a classifier from each data chunk. So let us say this is a week 1 data, week 2 data, week 3 data, and we build 3 models. This is our training data, and ensemble size is 3. So 3 models will be built, and then next chunk arrives. In this chunk we may have say 1000 data points. So we have 1000 data points in this chunk, and we will take each data points from this chunk, and this is a now test chunk. So far you build a model from this training data, and in the ensemble we keep those models. Now D4 chunk, I mean week 4 data arrives, which is a test data, and 1000 data points we have in the D4. You will take each of the test data points from D4 and try to predict using this ensemble. And what the ensemble has? Ensemble has 3 models, and each of the model will come up with a prediction for the test, each of the test data points, and we do the majority voting, what I showed you previously, right. So this way each test data points will take and apply the majority voting and do the prediction. And now after prediction you may have some ground truth on the D4 data points. Time passes, human will provide some label data on the D4 chunk, and what you need to do? You need to update your model or ensemble.
How do you know what is the best classifier ensemble? Like,
Yeah, that you have to do by experiment. So what we observe, if you use ensemble size 1, it will not help. Ensemble size 3 or 4, 5, these are reasonable numbers, but if you put ensemble sizes very big, that may not help either. So you have to go in the middle, not too, ensemble size should not be very small and should not be very large also. And again, which is the right number, you have to do experiment on your own data set. It varies from data set to data set. Some data set 3 might be a good as an ensemble size. For some data set maybe 4, 5, something like this. Okay, so D4, what will happen now? D4 will have some label data. So now D4 we build a model, and the model will be, so we build a model from D4, which is a C4. Now there are various policies you can adopt to update your model. One policy, some of you already pointed out, that why don't you discard the oldest model. Which one is the oldest model in the ensemble now so far? We build C1 from the oldest training data points, right? So we can replace C4 with the C1. So C1 will be discarded and C4 will be in the ensemble. Now my question is, why I need to do a replacement? Why I simply add the model into the ensemble? So that way the ensemble will grow indefinitely, right? If you do not replace a new incoming model with the existing one, then the ensemble size will grow over time. That we don't want. And some of the models anyway will be obsolete, right? So one policy is, so that's the motivation why you need to keep the ensemble size fixed. And now the question is, how do you want to find the victim or replacement? So one possibility is what some of you already pointed out, that discard the oldest one. So in that case, C1 will be thrown away and C4 will be in. That's one way you can do it. I'm not saying that's a bad, that you can try. In our case, we try a little bit, we claim ourselves is a better method, but you can try various options. So what we try in our case, we have a C1, C2 and C3, right? And which one is the most recent training chunk here in this case? No, most recent training chunk. So chunk is a D1, D2, D3, D4. So which one is the most recent training chunk? So in this case, we build a model from the D4 training chunk, right? So D4 is the most recent training chunk. So in that case, okay, so I'm saying most recent chunk is D4, and from there we build a model C4. So what I will do, and in the ensemble currently what I have C1, C2, C3, and ensemble size is 3. We want to keep. And in the ensemble we have so far 3 models are built, C1, C2, C3, and most recent training chunk is D4. I need to find a replacement. Basically, I want to add C4 here, and by replacing one of the existing models. So what I will do, I will calculate the accuracy of each of this model on the most recent training chunk D4. Recall that this training chunk, what we have in the training chunk? We have the each data points, independent variables and their values, and the class label or the dependent variable, right? So basically we have the data points and corresponding class label. So now we will take each data points and the model will come up with a prediction, right? C1 will come up with a prediction from the, let's say in this case we have a 1000 data points. Each of the training data points from the D4 will take it, and then C1 will come up with a prediction, and then we have a label ground truth also, right? Since we have a ground truth, what we can estimate? we can estimate this model's accuracy. Do you agree with that? I said this is the D4 is the most recent training chunk. That means we have the data points along with the class level. Now, each of the model from the ensemble will come up with a prediction, and then since we have a ground truth, we can also estimate from there each model's accuracy on this most recent training chunk D4. And according to this diagram, okay, so we will calculate the accuracy on D4 training chunk. Accuracy of C1 will be calculated, accuracy of C2 will be calculated, accuracy of C3 will be calculated. Let us say we found accuracy C2 is 0.4, 0.8. So, which one is on the D4 training chunk, which one accuracy is the lowest or the worst? C2. Among these three classifier C1, C2, C3, which one is performing worse on the most recent training chunk? C2. So, therefore, C2 will be thrown away and C4 will be in. That way we update the model. Is it clear? But again, you can discard the C1 simply and C4 can be in. There is a various policy you can adopt. But in our work, we adopted that way. We will focus on the most recent training chunk, and based on the most recent training chunk, we in the ensembles, each of the models accuracy will estimate, and then which model gives you the lowest accuracy, that will be thrown away, and the new model will be in the ensemble. So, after that, we will have a D5 training data, not training data, D5 will have a test data points. We will take it and do the, using this updated ensemble, we will do the prediction. And then time passes, you may have some ground truth on the D5, then you will build a model from the D5, which will be C5. And now we need to find a replacement for C5, right. So, we have to replace one of them, and what you will do? You will each in the ensemble, each of these models accuracy will be calculated on the most recent training chunk D5. So, in that case, you will calculate the accuracy of which one? C1 accuracy of C3 accuracy of C5, where the training data will be used, D5 chunk training data, right. So, this is your training data will be used to calculate the accuracy of each of this model. And in this case, I do not know which one is doing worse. Okay, this diagram has a problem. So, here now let us say C3 is doing worse. So, in that case C3 in the ensemble, what will happen? We will keep C1. Okay, I think I made a mistake, right. This will be C4, right. Very good. So, C4 and let us say C3 is doing worse. So, then C1, C4 and C5 in the ensemble we will keep it. So, in the ensemble we will keep C1, C4 and C5 now, and then using that we will try to predict these 6 test data points. So, okay, so I think you understand the key points. So, the key point I am trying to make here is the following. So, first we will do when the test data comes in the stream, we will do the prediction, and for the prediction we are going to use ensemble to apply the majority voting type of things. And then time passes, you may have some ground truth in that chunk. So, from there you want to build a model. Once you build a model, then you need to find a replacement in the ensemble. For the replacement, there are various policies we can adopt. One policy is discard the oldest model, or the model which is trained on the oldest data, that will be thrown away. That is one policy. In our case, we use different one. We can basically each models we calculate the accuracy on the most recent training chunk, and whichever gives you the lowest accuracy, that model will be discarded from the ensemble, and the new model will be in. Now, if you remember, I tried to say that stream has three problems. I listed 3 challenges. The first one is infinite length issue, and the second one is concept drift, and third one is concept evaluation or novel class. So, now I will argue that infinite length issue and concept drift can be handled by doing this. How? Infinite length means you cannot keep all the raw data in the main memory. So, here when you process the data, you do not process all the raw data. How do you process the data? In periodical basis, you process a portion of the data chunk by chunk. So, that means only a few points will be loaded from the disk to the main memory, or in the main memory you will keep only not the whole stream, you will keep only the micro batch or the batch. So, that way we handle the infinite length issue, and then we continuously update the model, right. So, in that case we can say that we are not perfectly addressing the concept drift entirely, but we handle concept drift some extent. Do you have any question so far? Okay, now the third challenge what we address, we will talk about that more details. Okay, so that is our work. So far what I presented, that is existing work, and this is the work we did, and I think we did a very good work, but anyway. And so, here I tried to tell you before that novel class or concept class concept evaluation is happening here. Let us say we have a 2-dimensional data points without loss of generality, and this is a one particular training data we have. So, we will build a model like this. So, basically it is a decision tree, right. Now, when the test data comes, what will happen? Some of them will, based on this decision tree, some of them will be misclassified as a positive class, some of them will be identified as a negative class. So, all of this test data points should form a brand new class, but according to the current stream classification or the machine learning technique, they will classify this X will be identified as an existing class, either positive class or negative class. But I am saying this X should form a brand new class or emerging class. Now, our goal is to identify those brand new class or emerging class in the stream. So, do you know why this is happening? Because the way we construct the decision boundary here is at the coarser grain. So, you can see there are a lot of unused space, that way the decision boundary is constructed. Now, the point falls into this area, then it will be misclassified, right. So, similarly here. So, our goal is to identify or construct the decision boundary at the finer grain instead of coarser grain. And for that I am going to introduce you some concept called Q nearest neighbor principle. So, if I ask you, can you tell me if we are in what dimension we are with 3-dimensional space, right. So, let us say if I ask you find the 2 nearest neighbor from me, who will be my 2 nearest neighbor? Obviously, you 2, right. How do you determine? Basically, from the computer perspective, we will calculate the distance from you and me and from everybody, and then find the shortest one is this. So, similar idea here. Let us say if I ask you Q nearest neighbor of X within the class C. So, let us say this is a positive class, this is a negative class, and this is a black dot represents some outliers. I haven't explained how do I get this, but with respect to this, if I say that what will be my give me the 5 positive nearest neighbor with respect to this point. So, what you will do? You will calculate the distance between this, distance between this, distance between this, distance between this, and then you will sort all of this distance for the positive class and take the 5 short 5 shortest one, right? That way you will find that this is my 5 nearest neighbor. Similarly, with respect to this 5 nearest neighbor for negative class will be something like this. And if I say 5 nearest neighbor with respect to black dots with respect to this, with respect to x, I want to find the 5 nearest neighbor from the black dots. So, this will be my 5 nearest neighbor. So, that way we define the neighborhood. Is it clear? That terminology I am going to use. So, again for nearest neighbor for a given class, you will calculate the distance between the point what you are considering along with the class instances and find the q and sort them based on the distance in increasing order and choose the top q, something like this. So, then now how the whole classification process works, I will tell you in a minute. This diagram tells you. So, here data are continuously coming, right. So, if the training data is test data is coming, what we will do? First, we try to determine whether the test data is an outlier or not, and for that we are using the ensemble based model. If the model say is an outlier, then we buffer it and then try to determine whether it forms a novel class or not. If it is not an outlier, then it will be classified as a existing class. So, what I meant, so recall that we have in our classification process we maintain ensemble. Ensemble size is fixed. In this case, ensemble size has L equal to 3, let us say. And then when the test data comes, we will each of this model will come up with a prediction, and in this case the prediction will be 2 levels. First, we try to determine whether the incoming test data is an outlier or not. I will explain that outlier detection in a minute. If it is an outlier, then we buffer it, and if it is not an outlier, then it will be classified as an existing class. Let us say existing class, so far we see class A, class B, class C. It will, but the test data will be classified as an existing class A or class B, class C. But if your test data belongs to a novel class, let us say class E, which we have not trained our classifier so far, our ensemble has not been trained with that class. So, in that case our goal is to determine that as a outlier. And again in our case, when we assume that when the novel class will emerge in the stream, it will not emerge as a single instance, it will emerge as a group or a number of instances will have that characteristics. On the other hand, if it is a training data, then we will build the model and the model will new model and the model will update the ensemble. Basically, we will find a replacement, replace it with the new model. So, here I will show you more details of our algorithm, then I will explain more details. Pseudocode may not be very clear, but here first the test data comes, we try to determine it whether it belongs to the existing class or not. And if it belongs to the existing class, that is fine, otherwise we will buffer it, and then when the okay. So, here when that okay. So, the steps is this: when the data points are continuously coming. So, first we try to determine whether the incoming data point is a novel class or not, or existing class, that this part of the code will do that. And then time passes, we may have some ground truth. So, we will update so we will build the decision boundary and update the model. This type of thing is going on here. So, I will explain those in details in a minute. So, first we do the testing, and in the testing we do the novel class detection plus existing class classification. And then time passes, you may have some ground truth. Once you have a ground truth, we will basically train a new model, and that model will update the ensemble. So, how we do the classification and the novel class detection, that I will explain now in details. This method is a non-parametric. We do not assume any underlying model of the existing class. There are 3 steps. The first steps, we do build the decision boundary at the finer grain. So, I try to criticize that the way the decision tree is constructed at the coarser grain. So, here we will create the decision tree at the finer grain with the help of clustering algorithm k-means, for example. And then test data comes, we will do the determine whether it is outlier or not. If it is an outlier, then we will try to determine this outlier forms a brand new class or emerging class. So, these are more novel class detection steps. So, second and third are novel class detection steps, and the first one is more build the decision boundary or training case. We want to during the training we want to build the decision boundary at the finer grain. So, let me explain each of these steps in details. So, first we want to build the decision boundary at the finer grain. So, just think about this. This is your one particular chunk training data in a 2-dimensional space, positive class and negative class. If you apply the decision boundary, if you apply the decision tree, it will construct a 4-quadrant like this. So, it will construct the decision boundary at the coarser grain, lot of unused space. So, what you will do, we will apply the clustering algorithms. Just think about, in this case, we have total 1000 points, 1000 points, and we have total 2 classes, positive class and negative class. So, here we have 400 instance, here we have 400, here we have 100, 100, total 1000 instance, right. And recall that I try to introduce you when I talk about this anomaly detection here, IoT data anomaly detection, I introduce you the k-means clustering algorithm. Recall that. When is it? On Tuesday, right? Tuesday? No, Wednesday. Yeah, Wednesday morning I introduce you the IoT stream analytics anomaly detection. So, there I introduce you the clustering algorithm k-means. So, here I will apply the k-means clustering algorithm. So, I am saying I give you 1000 points, ask you build 100 clusters, and I know that from in this toy example 400 belongs here, 400 belongs here, 100, 100 here. So, when you run k equal to 100 clusters, what do you expect? Proportionately 40 clusters will be built here, 40 will be built here, 10 will be here, 10 will be here, that total number of cluster will be 100. So, in that case what we keep, we do not keep the raw data, we keep the cluster centroid. And then, so you know that when you build the clusters in k-means, what type of information we keep? We can keep, each cluster will have a centroid, right, and then we can keep the cluster radius. How I determine the cluster radius? Basically in this cluster, which one is the farthest point, that will be the radius, right. So, we will keep the cluster centroid as a vector plus the radius information and some other statistical information. And then, so that way we call it, so in the past we used to keep only the decision boundary at the coarser grain by, we keep the decision trees rules, right, in the past. Now, instead we are trying to model this as in the finer grain. So, we will keep track of the each of these clusters centroid and the radius information and maybe some other statistical information, that we call it pseudo points or pseudo clusters. So, now previously when you build the model used to keep track only the model, in the model we used to keep track of the all these rules. So, if it is a decision tree, we will keep track of the rules. Say if the points is less than x1 and less than y1, then this part will be known as a, in the past when you build the model, what we keep in the model? We keep the model like this. If x1 is x1 and y is less than y1, then it will be known as a positive class. So, that way in the model we keep track all of this model we built CI in the ensemble, that way we will keep track the information. Now, what we are doing in the model, we are not keeping this type of information, because this does not help you to find the novel class or emerging class. So, what we try to keep in our model now is this cluster centroid, each cluster centroid and the radius information and so on. So, now the model will have, each of the model will have what? In this case 100 clusters, and each clusters we will keep track of the centroid and centroid information plus the radius information. So, now the model will have, in this case, in this toy example, model will have how many entries? Will have 100 information like this, 100 records. Yeah.
So wouldn't you also need a priority of the centroid cluster? And the reason I say that is because you've got them overlapping in all of the areas. So which one, if something if a data point appears in the center of two circles,
I mean overlap scenario?
which one does it take priority for?
So, okay. So, if you remember k-means clustering algorithm, the way k-means cluster is built, where we always assume that a point will belong to exactly, a point may belong at most one clusters. It is not a fuzzy clustering or is a hard membership. So, that is why in this case that is not, although in the diagram is confusing, you are thinking about overlapping, but in our case when you build the k-means clustering algorithm, so there each point will be assigned to at most one clusters. So, that way that issue will not come. But yes, if you consider the fuzzy clustering, then yeah, then we have to take into consideration that factors. Okay, now I am going a little bit slow, but anyway. So, this way from this training data we will build a model. Again recall that this model have a 100 clusters. So, the model will have a 100 cluster information. And then we discard all the raw data points. We do not need to keep track of the raw data points, we just keep track of the cluster centroid and the radius and so on. Now, when the test data comes, so that way if you remember I said there are 3 steps, right. The construct the decision boundary at the finer grain. So, this way we construct the decision boundary at the finer grain, and this finer grain will help us to find the outliers. And then now step 2 and step 3 we will do the outlier detection, and step 3 we will try to determine whether novel class is emerging or not. So, now this is one particular model or chunk. So, test data comes, x is a test data. So, what will happen in this case, this x, you will calculate the distance between x and this cluster radius, I am sorry, this cluster centroid. So, that distance you will calculate, basically you will take each point, test point x, and calculate the distance between this and the each cluster's centroid, and you will observe that this x and then this cluster, the distance between this two, this cluster centroid and this x is smaller than the radius of this cluster. Therefore, I can say that this x is covered by this cluster. So, that means this x will be identified as a existing class instance. So, it will be part of the whatever the this cluster has class level, this x is that contains that class. Now, if you remember I said clustering is unsupervised, but here we are trying to use some sort of semi supervised. So, what will happen? Okay, so, I said we keep track of the cluster centroid information, radius, and then other statistical information, maybe the class level. How can I assign the class level for a cluster? So, let us say this cluster has a 10 points, 8 of them belong to the positive class and 2 of them belong to the negative class. So, what class label I can assign to this cluster? Positive, right, due to the majority rule. So, similar idea here will be used. So, using the majority rule, I can assign the class label for each cluster. So, now when the test data comes, like x, in this case x is covered by this cluster, then this cluster has some class label, x will be assigned to that class label. On the other hand, this x is not covered by any of these existing classes clusters. Therefore, this x will be known as a outlier. This case it will be known as a raw outlier, and this is one particular model we built. And then keep in mind that we have L number of models in the ensemble. So, we have a test data comes, and each of the model will come up with a prediction, and internally the model, each of this model will have this. It will have a bunch of clusters information, and then from there we try to determine whether it is covered or not. If it is, say, all of the models say is not covered by any of this, all of the models say that incoming test data is not covered by any of the existing classes cluster, then it will be known as a filter outlier. So, that way we did it. Now, you may say, why don't you, once we identify an outlier, why don't we immediately say that this outlier will form a brand new class or emerging class? Because it is possible that this filter outlier may be a potential novel class instance, but also it may happen due to the concept drift or due to the noise. So, we have to isolate those scenarios. So, now when you build the clusters, so whatever I covered in this workshop, some of the knowledge will be useful now. So, when we say that we build a cluster, and I want to say that this is a good quality cluster, so how I can justify it? I give you a bunch of data points and you build a clusters, and how do you justify that you have a very good quality clusters? Because we don't have a class level, right?
Compact the clusters are.
Huh?
If you have a bunch of clusters that sort of bump up against.
Right, yeah, if it is a, if the each clusters are within the cluster, the points are very close together. Basically, intra-cluster distance is small and inter-cluster distance is big, then it shows that you have a good quality clusters, right. So, that we try to capture it using Shillud coefficient. So, there is in clustering, each point we can determine the Shillud coefficient. If the Shillud coefficient values tells you that whether the points are well separated from the other cluster, and at the same time they are close together or not within the same cluster. If that is the case, then it is a good quality cluster. So, here we are going to use that property. So, the idea here is, okay, let me explain the first theory, the high level big picture first. So, here these black dots we call it outliers, right. So, you understand how I determine the outliers, right. How do I determine outliers? How do I determine outliers? So, when the test data comes, I will see whether it is covered by any of the classes clusters or not. If it is not, if all the models say they are not covered by any of the existing classes clusters, then this will be known as a outlier. So, now this is an outlier, right. So, the idea here is, if you have a bunch of, in this case the black dot represents the outliers. So, the idea here is, if these black dots form a noble class, then the idea is this: these black dots, if they form a noble class, they will be close together, and at the same time they will be far away from the existing classes instances or existing classes clusters. If that is the case, then we can say that these black dots will form a noble class. So, the idea is, when a noble class is emerging in the stream, those points will be close together in the stream, and at close together means in a high dimensional space they will be close together, and at the same time they will be far away from the existing classes clusters. So, in this case I said these black dots are outliers. Now, I want to determine whether these black dots will form a brand new class or emerging class. So, what I am saying, these black dots will be close together in the multidimensional space, and at the same time they will be far away from the existing classes clusters. Existing class means positive class and negative class. If that is the case, then I can say that brand new class is emerging in the stream. So, again, when the novel class instances are emerging in the stream, they will be close together, and at the same time those points, novel class instance points, they will be far away from the existing classes clusters. If that is the case, then we can say confidently that novel class is emerging. Yeah.
With this particular approach, you have to, the assumptions are that you don't have a high dimensional space, I'm saying, because you're dealing with a lot of distance methods. And the other thing is you have.
No, I assume that is a high dimensional space.
Well, like, is there a limit? Like, so if I had, 100,000 different features, this would still work?
No, probably this may not work. Yeah, I agree with you. If it is, then it will be sparse and outlier detection may not work. So, for that I will show you after the break. There is another method especially for image and text. For high dimensional space, we may need to use some sort of different measurement. Yeah.
And the other thing is this also assumes that it's not just purely categorical or binary data. You have to have some like real information in there. So
Not
if you just had like just binary, if this here yes or no, if this here yes or no, this probably would work. Everything would be orthogonal to each other.
yes or no. What is yes or no? I mean class level or?
Just like is this thing Microsoft yes or no? Is this thing if Microsoft was a feature, if
Oh, I see. Okay. Yeah, it can work in the, if the feature is, let's say, where the product, the instance, you are saying instance has a bunch of features and some of the features is a binary, or yeah, it should work. But I agree with the first part what you said. If the data is each data points has a very high dimensional. Say here, when you test this algorithm, we tested it with a set 10. Each data points will have a 20 dimension, 30 dimension, or 100 dimension. This method works very well. But when you have 1,000 dimensions or more than 1,000 dimensions, very high dimensional data points, then in that case, this method doesn't work very well. So, for that we have a different solution. I will talk about that later, and that can work. I will show you that later, that it works very well for the images and the text data. Okay, so recall that we said test data comes. If it is a filter outlier, then we will take those filter outlier points and try to determine whether those points are close together or not, and at the same time they are far away from the existing class or not. That we try to capture it using the Q nearest neighbor Shillette coefficient properties. If I have once for each of these outlier points, we calculate the Q nearest neighborhood Shillette coefficient. I will explain that in a minute. And if you see that at least Q number of points have this characteristics, then we say that brand new class is emerging in the stream. That is the idea. So, again, what is the one of the weakness of this approach? You can say if you have a novel class is emerging in the stream, but the novel class has only one point, then this method will not work, the method I presented. We assume that when the novel class is emerging in the stream, it will not be emerge as a single point. It will emerge a number of points will have that similar characteristics. So, that is why I say single outlier alone does not imply a novel class. So, we need to examine the cohesion and separation. So, among the filter outlier points, and then so for that we define this property I told you, that Q nearest neighborhood Q nearest neighborhood property. So, when I say lambda C x is the set of Q nearest neighbor of x belonging to class C, and lambda O means set of Q nearest f outliers of x. So, now these are the all this is my test data x, I want to calculate the Shillud coefficient, right. So, I again recall that I try to tell you that these outliers, when they form a novel class, the idea is these outlier points will be close together in the stream. At the same time, they will be far away from the existing class instances. They will be far away from the positive class instance, they will be far away from the, in this case, negative class instances. If that is the case, then we can say that this outlier points will form a brand new class or emerging class. So, in that case, what we do for each of these x points or outlier points, we will calculate the Shillud coefficient. So, this way we define the Shillud coefficient. So, the idea here is for x we calculate the Shillud coefficient, and so Ax is the, okay. So, from the x we calculate the distance Ax, and then the b plus x is the how far is it from the positive class, and then we calculate the Shillud coefficient. If this value is greater than 0, what does it tell you? Can you tell me? For a given x, if this value is greater than 0, what does it tell you? It tells you that the point is, if this value is greater than 0, that means this x filter outlier is far away from the existing classes clusters, and at the same time this x is closer to the other outlier points, that we try to capture it here. So,
Does that make it novel?
Yeah. So, this will be a potential candidate for novel class. So, if QNSC is positive, it means x is closer to the other outlier points and then existing classes clusters. So, that we try to capture it. If you remember here, for each outlier points we calculate the q nearest neighborhood Shillud coefficient, and if you have at least q points, q is a parameter, in our case we set it q equal to 50. So, if you have 50 outlier points, then we call it those outliers, all of them, as a novel class. So, do you have any questions so far? And then for the ensemble update, what we do, time passes, you may have new data points will arrive, the new classifier will be built, here it is not shown for some reasons, we have to fix it. So, this some sort of cluster will be built, and then new cluster will be added here by replacing the M2. So, here we said obtain the accuracy of each of the classifier on the last label data chunk or the most recent data chunk. So, now I want to show you some results what we got by experiment. So, the first two data set are synthetic data set, and here we use 2 class and 10 attributes only, 250,000 instances. These are synthetic, and KDD, you know that the KDD data set is outdated now, but it is an intrusion detection data set. These are the attributes and 23 classes. Forest cover data set also we use. And this is our configuration, k equal to 50 clusters we build per chunk, and q is the minimum number of instances required to detect novel classes 50. Also ensemble size we use 6, and chunk size is 2000 instance will form a chunk. And ECS minor is our approach, and these are the 2 baseline approaches. And what is the baseline approach? It is a combination of weighted classifier ensemble, and then there is a novel class detection algorithm is there. And when we develop this technique, we are the first develop this technique. So, this is the, so we use, the problem is when you do the novel class detection in 5-6 years back, at that time only one group has done some work. So, this is the group. So, our case we need to compare our approach with them. So, for that we modify their technique slightly, because their technique works in a binary class setting, this one anomaly detection, and this is the work where they talk about concept drift in the data stream, but nobody has done the novel class detection. So, we combine these two and simulate the novel class detection and compare it with our approach. So, Mitchell came, she wants to take a picture and publish some article about our workshop. So, do you mind if you they want, or is not allowed? Or she can take your picture, only the top of your head, not the face. Huh?
We'd rather not have a picture. Oh, I'm just getting it.
Okay.
Okay, thank you.
Okay. Yeah, we want to advertise that I am doing a good work. Thank you. Yeah, Maureen told me that we should not take your picture. Okay, let me. So here, so the baseline all-Indus approach, we assume that there is only one normal class and all other classes are novel. So for that, so keep in mind that in our setting, we are not focusing on only two class problem. We are focusing on multi-class setting, right? Multi-class problem. So how we can address that issue? So what do we do? One approach is, let's say we have a class A, class B, class C in the stream. So we train our model with the class A, and the rest will be the outliers, something like this. So that way we keep the parallel all-Indus method for one for each class, or we can absorb everything together is one model, and then novel class will be treated as outlier. Okay, so the results will be reported in terms of the error. So now our goal is to detect the novel class, right? So when you do the novel class detection, what will happen? So test data comes, our model predicts it as a novel class, and the true level is also a novel class. In that case, it will be a success. But if the true level is a novel class and our model predicts it as an existing class, then it will be known as a false negative, right? So novel class instance will be misclassified as existing class, that is called false negative. On the other hand, existing class instance will be misclassified as a novel class, then it will be known as a false positive. And then false, this is a, let's say we have an instance belongs to class A and our model belongs to, predicts it as a class B. Both A and B are the existing class. So then in that case, it will be FE type of error. So based on that, we try to determine those errors. So novel class instance misclassified as existing class, that M new, and false new means existing class. Every time I fix it, I have to. So this is a false positive, and this is the false negative actually. The novel class instance, percentage of novel class instance will be misclassified as existing class, and percentage of existing class instance will be misclassified, falsely identified as a novel class, that will be a false positive, right? And this is the total error we try to report. So I will fix this slide later. Now x-axis represents the stream data are coming like this. So the time passes, you will have a more streaming data, and here you can see the novel instances are arriving like this. Time passes, you have more novel instances, right? Is a cumulative. Now if you use, so this is the total in novel class instances we have so far at this point, and now now if you use our approach, we miss only few novel class instances. So y-axis represents how many instances we miss. So it has a very low number. So on the other hand, the all-Indus approach, these two baselines, they have a very high error rate. So this case error rate is very high for the two baselines, and our method the error rate is very low. Thank you, Mitchell. And then we do the same thing for the KDD data set, and here the key slide, you can see these are the 4 data set we use, and this is the total error, and this is the novel class instance error, and this is a false positive. And XM is our approach, and these are the two baselines, and the lower the number is better. So in this case we use decision tree, and in this case we use the k nearest neighbor. Recall that we use the classifier, right, to build the model. So and you can see all of these cases our method is doing better than other approaches. So in terms of the speed, we are in the middle, so we can consume this 1000 data points by this time, and per second we can consume this amount of data. And okay, so here there are some limitation of this work. One limitation is we use the fixed chunk size, and sometimes we observe that concept drift can cause high false positive rate. And then already you pointed out that this method has a limitation when you have a very high dimensional data points, outlier detection may not work well. So that type of thing we need to address. And then we always assume that each data point have only one class level, but there is a possibility that a data point may have many class level, more than one class level, what we call it multi-level. So in our later work, I will show you how to deal with the false positive rate and how to deal with the dynamic chunks, how to deal with, instead of fixed chunk, we can develop dynamic chunk. So I want to give you a break. I took too much time. So after the break, I will start to speed up my talk, because I will have, today you have a lunch break will be a little bit later. So please, when we will start, we will start again, 10:45 or according to the schedule? Okay, let's meet at 10:50. Huh? Yeah, 10. We'll resume our meeting at 10:50.